Good afternoon. My name is Bharth Kumar. I am from Data Science Department. Today I am going to discuss about the concept of AVL trees. First of all, before that, first of all we will discuss about some of the basic concepts. So those are the basic concepts is, first of all, what is a tree? After that, next we discuss about what is binary tree, and next one is what is binary search tree, and next one is what is an AVL tree. After that, next we will discuss about what are the rotations that can be performed to AVL trees. So finally we will discuss about the insertion and deletion operations on AVL trees. So first we discuss about what is tree. So first we will discuss about the basic concepts are what is tree, and the second one is what is binary tree, and third one is what is binary search tree, and next fourth one is drawbacks of binary search tree, and next fifth one is what is an AVL tree. And sixth one is what are the rotations we performed on AVL trees. And last one is we can performing the operations are insertion and deletion operations. So first we discuss about these concepts. So first of all, what is meant by tree? A tree is represented as T. It is containing vertex set as well as edge set. The vertices are nodes connected by the edges. So it is represented as tree. Then it is mainly satisfying three properties. What are the three properties is? So the first property is it contains a specially designated node. That node is called as root node. So second point is every node except the root node, it containing exactly one parent. And third concept is every node can containing at most two childrens. So these are the basic concepts of tree. In the tree, so here we are consider so many childrens. So two or more children. So in the tree, so here we are consider any number of childrens. So there is no restriction to store the elements. So here we can store the elements in any order. So for suppose we can store the elements is 30, 25, 40, 16, 19. So here we are not maintaining any order. So here we can store the elements in any order. So there is no problem in tree. Whereas in binary tree, so the second concept is binary tree. A binary tree is a tree. Initially it is empty. Initially empty is nothing but it is containing only the root node. If it is not empty, then it contains at most two childrens. So this is the left child is one and another one is right child. So here also there is no restriction to store the elements. So here we can store any number of elements, that is we can store the elements in any order. So for suppose here we can store 30, 40 and next one is 25. So there is no restriction. So here we can store any order we can store the elements. And next third one is binary search tree. A binary search tree is a binary tree. Initially it is empty. If it is not empty, then it satisfies mainly four properties. So those four properties is every element in the binary search tree has a distinct key element. So here every binary has a distinct. Distinct means, so here every key element as different elements. There is distinct elements. And the second one is the element in the left hand child is less than the root element. The element in the left hand side is less than the root element. And third property is element on the right hand side is greater than the root element. And next, fourth point is the left and the right childs are also binary search trees. So these are the four properties that can be satisfied by the binary search tree. Now let us see the drawbacks of binary search tree. So now let us take it as one example. So here I am taking one example is 30. So this is the binary search tree. In that binary search tree, every element in the left hand side is less than the root element, and at the same time every element on the right hand side it is greater than the root element. So now let us find the time complexity of this problem. So in that, so for suppose if you want to search the element is 29, so first it is considered as the key element is 29. So first it is checking the element, that is root element is 30. So it is less than the root element, then it is searches left hand side. Again it is search the 25. So 25 is by comparing to 29, so it is greater element, so it is searching the right hand side. So 29, so now it is element, so here we can find the element. So here search is successful. So the maximum number of comparisons are, this is the first comparison, second comparison, and next one is third comparison. So for suppose if you want to search 40, the key element is 40. So here first it searches the element 30, that is root element. So after searching the root element, so it is the bigger element, so now it is comparing to right hand side. So here it is check the element, that is 40 is equal to the 40. So here it is searching the element. So here element is successfully searched. So here the comparisons are, the maximum number of comparisons are 2. So here if you want to take any array, that array containing n elements, so for suppose here we can consider as this is the array. So in that array it is consisting of n elements, that is 1 to n elements. So the binary search tree is exactly searching off of the elements, that is, so it can be divided into two parts. Okay, so the first part containing t of n by 2 and the second part containing the t of n by 2. So by adding this t of n by 2 plus t of n by 2, then it is t of n. So that is equal to t of n. Okay, so the recurrence relation for this problem is t of n is equal to t of n by 2 plus 1. By solving this recurrence relation, then we can get the time complexity is big O of log n. Big O of log n, that is t of n is equal to big O of log n. So for suppose if we are considered the array elements, there is 10, 20, 30, 40, 50. So there is, so here we can consider the array element is sorting order. So here by inserting these elements, then it is the order, there is 10, 20, 30, 40, and next one is 50. So here the time complexity is the maximum number of comparisons. So it is equivalent to total number of elements. So for suppose if we are consider n elements, so the maximum comparison is taken as n elements. So it is similar to linear search. So this is the drawback. Okay, so here the problem will be occurred whether the binary search tree is either left skewed binary search tree or right skewed binary search tree. So the problem can be occurred. So this problem can be overcome by using AVL trees. By overcoming the AVL trees. So first of all, what is AVL? So there are three scientists that can be proposed the AVL trees. Those three scientist names is, so first one is Adelson, second one is Welsky, and the third scientist is Landis. These three scientists that can be proposed the AVL trees. AVL tree is nothing but it is a self-balanced binary search tree. So it is nothing but it is a self-balanced binary search tree. So here we can find the balancing factor of each node. So the balancing factor is calculated as height of the left subtree minus height of the right subtree, which is less than or equal to -1, 0, 1. Okay. So whenever the range is exceeded, obviously the binary search tree is unbalanced. So if the binary search tree is unbalanced, then it is converted to balanced search tree. So here we can find the balancing factor of each node. The balancing factor cannot be exceed -1, 0, 1. Here next one is, so here whenever the binary search tree is unbalanced, now we can performing the rotations. So there are mainly 4 types of rotations. Those 4 types of rotations are, one is LL rotation, and the second one is LR, and third one is right left notation, and last fourth one is right rotation. So these are the 4 rotations that can be used to unbalanced tree will be converted to balanced. The LL rotation and RR rotation is called as single rotations, whereas in LR rotation and RL rotation is called as double rotations. So this is the single rotation, and these two are double rotations. Now we are going to discuss about these rotations. So first one is LL rotation. Now let us consider the elements 3, 2, 1. Now apply the binary search tree. Okay. Now first 3 will be inserted. Next, the balancing factor of 3 is height of the left subtree is 0 and height of the right subtree is 0. 0 minus 0, 0. So there is no problem can be occurred. Now we can add 2. By comparing to 3, it is the smaller element, then it is added into left hand side. Now we can calculate the height of the node. That is nothing but balancing factor. There is 3 is height of the left subtree is 1 and height of the right subtree is 0. There is 1 minus 0, that is equal to 1. Next one is height of the left subtree is 0 and height of the right subtree is 0. 0 minus 0, 0. So there is no problem. Now we can insert one, which is by comparing to 3, it is smaller element, then it goes to left hand side. Again it is comparing to 2, it is smaller element, again it is going to the left side. Now here the problem will be occurred. So the problem is height of the left subtree is 2 and the height of the right subtree is 0. 2 minus 0, there is 2. And next one is height of the left subtree is 1 and the height of the right subtree is 0. 1 minus 0, 0. And next one is height of the left subtree is 0 and the height of the right subtree is 0. So here the binary search tree is unbalanced. Now we can convert this binary search tree is converted into balanced. So how it is converted? By using LL rotation. There is, so here we are arranging order is left hand side. Now we can performing the LL rotation. In that LL rotation, now we can pull the elements. That is, we can pull the element on right hand side. Okay, it is nothing but pull the element on right hand side. Now let us assume that, so this is the bar. So in that bar, now we can pull the element. then 2 will be goes to root element and 3 will be goes to child element. So now it is converted to, and left hand element is 1 and right hand element is 3. Now we can check the balancing factor of each node. So height of the left subtree is 1 and height of the right subtree is 1. 1 minus 1, that is 0. Height of the left subtree is 0 and height of the right subtree is 0. 0 minus 0, 0. Similarly, height of the left subtree and height of the right subtree is 0 minus 0. So now it is balanced. So this is, first one is LL rotation and the second one is LR rotation. Now consider the elements 3, 1, 2. So first we insert 3. After that next 1. By comparing to 1, it is smaller element, then it is goes to the left hand side. Now comparing to 2 will be comparing to 3, then it is smaller element, then it is going to the left hand side, and comparing to 1, it is bigger element, then it is placed on to the right hand side. It is nothing but left, and next one is right. So the height of the left subtree is 2, total elements are 2 and minus 0. The height of the right subtree is 0. So here the balancing factor is 2 and the height of the left subtree is 0 and the height of the right subtree is 1. The balancing factor is minus 1. So here the height of the left subtree is 0 and the height of the right subtree is 0. 0 minus 0, there is 0. So here now we can perform, now we can convert into balance. So this is unbalanced, now we can convert it into balance. So first we needed to perform the left rotation. After that next we can performing the right rotation. So in that left rotation there is, so 2 will be push and 1 will be goes to the left hand side. There is 3, 2 and 1. Again the tree is unbalanced. Now it is converted to balance. Now we can performing the operation is right rotation. There is 2 will be goes to root node and 1 is the left node and another one is right node. So now it is converted to balancing. So now we can perform the another rotation is RL rotation. Now let us consider the elements 1, 3, 2. 1 is the root node. Now we can comparing 3. It is the bigger element, then it is goes to right hand side. Now comparing 2, it is the larger element, then goes to right hand side. By comparing to 3, it is the smaller element, next it is going to the left hand side. So it is nothing but R and next L. So it is nothing but RL rotation. In that RL rotation, so first we needed to perform the right rotation. After that next we can performing the left rotation. Now 2 will be pushed the 3. So now we get the, after pushing, then we get the binary search tree is 1, 2, 3. Still it is unbalanced. Now it is converted to balanced. So now we can performing the rotation is L rotation. So here we can performing the right rotation. After that next we can performing the left rotation. Then it is 2 and next one is 1, 3. Then it is going to the balanced. And last rotation is RR rotation. There is right rotation. Now consider the elements are 1, 2, 3. So 1 is the root element. Now comparing 1 with 2, it is bigger element, then it is placed on to the right hand side. Similarly 3 goes to the right hand side. Now we can performing the operation is left rotation. After that next it is converted to balanced. So here we are performing 3 rotations, total 4 rotations. So those 4 rotations are, first one is left rotation, and second one is left rotation, and third one is right left rotation, and fourth one is right rotations. Now we can apply these rotations to one example. So this is the previous JNTU problem. So here we can solve this problem. Okay, so first we needed to insert 12. Every insertion operation, so first you needed to check the balancing factor of each node. After inserting 12, so now we can check balancing factor. There is left hand side and right hand side. Left hand side there is no children, and at the same time right hand side there is no children. So here the balancing factor is 0. So now we can insert 30. So by comparing to 12, it is bigger element, then it is going to the right hand side. There is 30 will be stored. Next, check the balancing factor of each node. Height of the left subtree is 0 and height of the right subtree is 1. 0 minus 1 is minus 1. So here the height of the left subtree is 0 and the height of the right subtree is 1. 0 minus 1, that is minus 1, and the height of the left subtree is 0 and the height of the right subtree is 0. 0 minus 0, 0. So there is no problem. Now we can add the another element. There is nothing but 36. So by comparing to 12, it is going to the right hand side. Now it is compared to 30. Again it is storing into right hand side. That is 36. So it is unbalanced. Now check the balancing factor of each node. So now balancing factor, there is height of the left subtree is 0 and height of the right subtree is 2. So here minus 2, and next one is height of the left subtree is 0 and height of the right subtree is minus 1. So this is minus 1. So this one is 0. So here the tree is unbalanced. Now the tree will be converted to balanced. So here we can applying the rotation is RR rotation. So now we can shift the element from left hand side. Then after conversion, 30 will be the root node and the left child is 12 and right child is 36. So now it is going to the balanced. Now we can add the another element, there is 18. By comparing to 30, it is the smaller element, then it is go to the left hand side. Now it is comparing to 12, it is bigger element, then it is stored into right hand side. There is 18. And next one is 25. Now we can add 25. So by comparing to 30, so here 25 is the smaller element, then it is going to the left hand side. Again by comparing to 12, it is going to the right hand side. Now comparing to 18, so it is the larger element, again it is going to the right hand side. There is 25 will be stored. Now we can calculate the balancing factor of each node. So here the height of the left subtree is 1, 2, 3 and the height of the right subtree is 1. There is 3 minus 1, that is equal to 2. And next one is height of the left subtree is 0 and height of the right subtree is 2. There is 0 minus 2, that is equal to minus 2, and the height of the left subtree is 0 and the height of the right subtree is 1. 0 minus 1 is minus 1 and height of the left subtree is 0 and height of the right subtree is 0. Similarly, height of the left subtree and height of the right subtree are 0. 0 minus 0, it is consisting of 0. So here the tree will be unbalanced in two cases. One is left child and another one is root element. In that case, so first we can convert the unbalanced to balanced. So here we can consider as last 3 elements. That is, so here we can consider as last 3 elements. After converting this, then it is, now we can check whether it is balanced or unbalanced. So here we can performing the operation is RR operation. So now we can performing, there is, so here the root node is 30. Now we can performing the left rotation, then 18 goes to root node and the left child is 12 and the right child is 25. Now the right child 36. Now check the balancing factor of each node. So here the height of the left subtree is 2 and the height of the right subtree is 1. So here the balancing factor is 1. Height of the left subtree is 1 and the height of the right subtree is 1. Then the balancing factor is 0. Similarly 0, 0, 0. So now the tree is balanced. Now we can insert the another element. There is 25. 30 is another element is 9. Then it is comparing, it is smaller element goes to the left hand side, again go to the left hand side, again we can take it as 9. So now we can check the balancing factor of each node. So in that balancing factor, so here height of the left subtree is 1, 2, 3 and the height of the right subtree is 1. 3 minus 1, that is height of the balancing factor is 2. Similarly height of the left subtree is 1, 2 and the height of the right subtree is 1. So here 2 minus 1, 1. Height of the left subtree is 1 and the height of the right subtree is 0. Then the balancing factor is 1. So here height of the left subtree and height of the right subtree is 0, 0. So here also 0, here also 0. Again the tree is unbalanced. So in that case, so here where it is occurred, so here it is occurring in 30. So now we can rotating. So now consider these 3 elements. So now 18 will be goes to the root node. So 18. So the left hand node is 12 and the left hand node is 9. Now 18 is goes to the root node. So in that case 25 goes to the right hand side. So here the element is 30 and the second one is 36. So where the place is here, left hand side. So now we can allocate, there is 25. So now we can check the balancing factor of each node. So in that balancing factor, there is height of the left subtree is 2 and height of the right subtree is 2. 2 minus 2, that is 0. Here also 0. Here also 0, 0 and height of the left subtree is 1 and height of the right subtree is 0. 1 minus 0, 1 and height of the left subtree is 0, 0. 0 minus 0, that is 0. Now we can insert another element, there is 4. Now comparing to 18, then it goes to left hand side, again goes to the left hand side, next again it is placed on to the left side. Now calculate the balancing factor. So here height of the left subtree is 1, 2, 3 and the height of the right subtree is 2. So here the balancing factor is 1 and the height of the left subtree is 2 and the height of the right subtree is 0. There is 2 minus 0, 2. So here height of the left subtree is 1 and the height of the right subtree is 0. So here the balancing factor is 1. So again it is imbalanced. So here now we can convert the unbalanced to balanced. So here we can performing the operation is left rotation. So after conversion, nine goes to root element and the left hand child is 4, right hand child is 12 and next one is 30, 25 and next one is 36. So now we can check the balancing factor. In that balancing factor, so height of the left subtree is 2 and the height of the right subtree is 2. 2 minus 2, 0. Similarly 0, 0, 0. It is balanced. Now add the element 2. So now we can check the balancing factor of each node. Height of the left subtree is 1, 2, 3 and the height of the right subtree is 2. 3 minus 2, 1. And next height of the left subtree, height of the right subtree is, here it is 1, 1, 0, 0. So similarly it is balanced. Next add the 17. By comparing to 18, it is smaller element, then it goes to 9. By comparing to 9, next it goes to right hand side and it is placed on to right hand side. So next one is, next check the balancing factor, it is also balanced. Now let us consider 14. So in that case, so by comparing to 18, then it is smaller element, then it goes to left hand side, and 14 is the bigger element, then it is goes to right hand side. By comparing to 12, it is bigger element, then it is goes to right hand side, again it goes to left hand side. Now we can check the balancing factor. Here it is unbalanced. So here height of the left subtree is 0 and height of the right subtree is 2. 0 minus 2, that is 2. And the height of the left subtree is 1 and the height of the right subtree is 0. 1 minus 0, that is 1. So here 0. So here the tree is unbalanced. Now we converted this tree into balanced. There is, so here we can performing, there is nothing but right left rotation. So here first we need to perform the right rotation. After that, next we can performing the left rotation. So in that right rotation, there is 14 will be goes to here and 17 goes to child node. Next after rotation, there is, so 14 goes to root node, 12 goes to left child and 17 goes to right child. So after that conversion, so 18 is the root node and the left child is 9 and the left child is 2, 4. Next one is 2. In that, here we can performing the left rotation. After that, next we can performing the right rotation. So here the root node is 14 and the left child is 12 and the right child is 17. Next one is 30 and next one is 25, 36. So now we can add another element, there is 20. So by comparing to 18, so it is the bigger element, then it goes to right hand side. By comparing to 30, it is the smaller element, then it goes to left hand side. Similarly, next it is placed on to left hand side. Now we can check the balancing factor, everything is okay. So now finally we can insert 47. So it is bigger element, then goes to right hand side, right hand side. So finally it is storing into the element 47. So this is the final insertion operation. Now we can performing the deletion operation on 18 to 36. So first you need to delete. Okay, so first we delete the operation, that is 18. So here 18 containing two children, one is left child and another one is right child. So if you want to delete 18, so here we can take it as immediate predecessor or immediate successor element. So here we can take it as either immediate predecessor element or immediate successor element. So immediate predecessor element is nothing but the left hand side is, we can take it as larger element, and at the same time right hand side we can take it as smaller element. So that element is placed onto the root element. So for suppose if you want to remove 18, then it is replaced to immediate predecessor element, there is nothing but bigger element, there is 17 will be placed to here, or otherwise we can place 20. So any one of the element that can be replaced to here. So here I am replacing 20. So here 20 and next element is 9, 4, 2, 14 and the left hand child is 12. Now right hand side is 30, 25. So here we are placing 30. So there is no need to write. And next one is 36 and next element is 47. Now check the balancing factor of each node. So here the height of the left subtree is 1, 2, 3, and at the same time height of the right subtree is 3. So 3 minus 3 is equal to 0. So no problem here, also no problem. So here the tree is balanced. So it is balanced tree. So now we can delete the element 2. So 2 is nothing but child node. Okay, so here directly we can remove it. Okay, so there is no need to move the position. So finally we can delete it. Okay, so if the child node, if the tree, if you want to delete any node, that node is child node, so immediately we can delete it, there is no problem. And last one is 36. So here it is containing the one child node, so this child node will be moved to the corresponding position. So finally we get the elements are 20, 9, 4, 14. After that left hand child is 12. The next one is 30, 25. After deleting 36, next it is placed onto here. So now check the balancing factor of each node. So here the balancing factor is everything okay. So finally this is the AVL tree. Okay. Thank you.